Great, thank you very much. Good afternoon and good morning and good evening, everyone. I think we're covering a lot of time zones today. I'm personally in Germany, and I know people are covering all the coast in the US as well. So welcome to our monthly Atmosphere Collaboration Team meeting. For those of you who are maybe unfamiliar with IARPIC, the Atmosphere Collaboration Team is a very nice mix of people from across university, government, and beyond, who are focused on atmospheric processes and problems in the Arctic. And we're currently transitioning between Arctic research plans, but we have a variety of different topics that we're attempting to focus on. And one of those is the topic that we're discussing today. We have two very nice presentations focused on atmospheric rivers and their role in governing Arctic climate and weather. This has definitely been a hot topic recently, more in the southern hemisphere. That's been in the news much recently with the impact of atmospheric rivers on the ice shelf down there. But certainly, it's played a very critical role in helping to govern Arctic processes as well. And so we have Bill Neff and Michael Tjernstrom joining us today to provide some presentations on this topic. And I will open it up quickly to Barry to let him introduce himself as well, and then we'll get on with the meeting.
Thanks, Heis. I'm in the NASA Atmospheric Composition Program and excited to kick off a new season of IARPIC Atmospheric Collaboration Team meetings. We're looking forward to this discussion, and I don't want to get in the way anymore. Thank you. And hopefully we'll have some chance for discussion at the end.
All right, thank you very much, Barry. So we'll get started with our presentations. Our first presenter is Bill Neff from University of Colorado and NOAA formerly. And Bill is going to talk to us today about the role that atmospheric rivers play in events in Greenland. So Bill, thanks for joining us today, and we look forward to your presentation.
Okay, let me get my share screen here. And go to slideshow. Okay, yeah, so this is, I'm trying to cover all the bases here in the atmospheric river title because there are heat waves, hurricanes, and all sorts of stuff affecting the Arctic. Got started on this back after the huge melt in 2012. And at the time, we wondered, well, where did the hot air come from that was melting the ice? And did a quick back trajectory and discovered it started in Kansas. It was the Dorothy moment when she said, Toto, I have a feeling we're not in Kansas anymore, but she forgot her parka. And at the same time that was happening, we noticed that there was this massive drought and heat wave in the Midwest that allowed the hot air from the Midwest to go over the Atlantic Ocean and then to Greenland. And initially this was attributed in a paper in 2014 to an atmospheric river. This is the SSMI imagery of the moisture in the atmosphere as it first hit Greenland and then went on to flood UK. Jean-Louis Bonnet did a paper, actually his PhD, published in 2015, doing analysis of water vapor isotopes and with a numerical model that included those to show that the origins of the atmospheric river lay in the South Atlantic. And then Kyle Mattingly did a very nice analysis. It was published in 2018, pointing out through a detailed analysis that ARs had increased in frequency since about the turn of the century. After this, then another paper was published by Lizzie Barnes' group at CSU that pointed out the difference between cyclonic and anticyclonic wave breaking and its impact on transport in the vicinity of Greenland. Essentially, anticyclonic Rossby wave breaking would transport moisture to the east, whereas cyclonic wave breaking would transport it to the west. You can see this visually. That's an interesting picture I found of Greenland there, but you can see during what they found during their analysis is that during the negative NAO, cyclonic wave breaking would transport more moisture along the west coast of Greenland, and which is consistent then with the increased mass loss along the west coast of Greenland, as well as consistent with John Louis' analysis of the isotopic and moisture transport documented through arrival at the NEAM site, North Eemian drill site in Greenland. So what we wanted to do was, rather than do a detailed analysis of the atmospheric rivers themselves, but look at ways to detect the transport of moisture along the west coast. So we essentially looked at reanalysis data at 2 points, one over the Labrador Sea and one more towards the Davis Strait, and looked at the airflow coming in there. This is a composite of a number of cases at 850 pascals of the wind. And what we discovered from that, looking at two sites, this is the distribution of wind speed and direction, and in colors are the total integrated water vapor. So you can see that, for example, at the tip of Greenland, wind speeds of 10 to 15 meters per second from the south-southeast, south-southwest, south-southeast, we carry most of the moisture along Greenland. As you move up to the Davis Strait, about 800 kilometers to the north and a little bit west of north, was much more focused. When we did the analysis, this is the composite from the data at the tip of Greenland. What you saw was, in fact, a low pressure system over the Labrador Sea and a high pressure over the Atlantic. And Michael Gallagher and our group at NOAA did this very nice analysis using a self-organizing map analysis, showing that, in fact, the maximum warming at Summit Station corresponded to this low pressure system just near the tip of Greenland, where the maximum warming at Summit was tied, in fact, to this synoptic pattern, which is exactly the pattern we see in the analysis above. We looked at that in a little more detail. Here's the atmospheric river going up the west coast. And here's a cross section from this little section right here, showing, in fact, it's a low-level jet carrying most of the moisture along the coast of Greenland. It's essentially a barrier wind carrying most of the moisture from the south. And if you look at precipitation rate, it's all concentrated along that coastline with a steep orography. Now, in 2018, Kyle Mattingly published this paper, and I was asked to comment on it by Nature Climate Change. And I had to do this black and white picture because they were worried about colorblind readers. But the interesting thing is that this case that I used as an example from Doyle 2015 sort of matched that inflow, this atmospheric river that was going up along the coast of Greenland. But what Doyle found in this case was that about 10% of the annual mass loss occurred in this one event over 6 days. And found that sort of interesting. So we looked at the melt patterns, and they start in the west, they spread along the west, and then they proceed along both the southeast coast and the west coast. And this corresponds to this pattern of rainfall at Kangerlussuaq on the west coast, where the rain is fairly heavy as about midpoint in the event. But then when we looked at the SSMI imagery for this, we saw that this atmospheric river came from the subtropics. You can see South America there, and Irene just off the coast of Cuba. And it's all part of this pattern of moisture moving to the north along the coast of Greenland. Now, at the time I did this figure to comment on Kyle's paper, I didn't look at it carefully at first, and it turns out Irene shows up there. And that was fascinating because it meant then that hurricanes are essentially part of this flow of moisture that goes into the Arctic. And this is an animation showing what happens with Irene. I put the melt map at the end of this episode up in the upper right, but you can see Irene moving along the east coast of the US, then through maritime provinces of Canada, and then eventually settling and stopping near the tip of Greenland. The cyclonic circulation around Irene then is bringing the moisture from the subtropics up around the southeast coast of Greenland and producing the melting you see on the melt map there. So it's very clear indication then of the effect of some of the hurricanes that can go up along, follow these high pressure patterns in the Atlantic and eventually wind up near Greenland. So we asked how often do these events occur? And we saw Irene in 2011. In 2010, there were two hurricanes that wound up over the Labrador Sea, Earl and Igor. The case for Earl, there was actually supplemental material in Jean-Louis's paper in 2015 from the Nîmes ice coring site that showed the evidence of subtropical air through both measurements of deuterium, the D-excess, the deuterium excess measurements there. Igor was sort of interesting because it brought all this moisture up in September to Greenland. And one of the people in our group, Solomon and Shoup, did this paper in Jazz describing the warm air advection over Greenland, but not associating it with Igor. So we decided, let's look at this in a little more detail. These are the hurricane tracks near Greenland from 1851 to 2019. And so a lot of hurricanes head to the north through the Atlantic. And so we looked at the period from 2000 to 2012 and this area of interest, this little box around the south of Greenland, and looked for events there. And what we found were two classes, one with direct impact, where the hurricane such as Irene actually makes impacts directly the coastline, and then other hurricanes that were generally embedded within this moist flow from the tropics, bringing moisture, but not retaining their low central pressure and so forth as they got close to Greenland. What we found was that generally there were one or two hurricanes a year over this 13-year period that would have an impact on Greenland. After 2012, the hurricanes didn't make it that far north. Recently, they've been picking up a little bit more, and we'll get to that. I want to also discuss some of these extreme events recently. When we first did the paper in 2014, 1889 was the last major episode. And since the medieval climate anomaly, when there was a lot of warming over regionally in the North Atlantic. And then came 2019. This is the picture of the Washington Post of the melting in Greenland and sled dogs going across through the water there, which was quite intriguing. And so we asked, what happened in 2019? Well, in 2019, in the middle of June, there were two major plumes of moisture. This is total integrated water here going to the north. There's one to the east and one to the west. The one to the east was interesting because it originated in a temperature anomaly just off the west coast, northwest coast of Africa, 10 degrees C temperature anomaly. The dry air off of Africa came out over the ocean, picked up moisture as it goes up, and then made this plume here. Now, this other plume is really interesting because it started in Tibet indirectly. And Lance Bossart did this really nice presentation at the EGU later that year that showed that this actually was initiated by an area of warm air that came out over the Pacific and essentially provided this wave amplification that then propagated to the east and brought this plume of moisture up to the maritime provinces and up the west coast of Greenland. So essentially it says the Arctic is not isolated from the things that happen from the tropics. Now the heat wave off of Africa then provided one of the melting mechanisms. Late in July then, there was this moisture plume that came up off around this omega block over Europe and brought all this moisture up and spread over Greenland. What's interesting about that case, that was essentially a 14 degrees C anomaly over wine country in France where the air originated and then spread over Greenland. So again, Greenland is not that isolated. And what's interesting about this is there were two melt episodes that summer. And Van Walden from Washington State did this nice presentation at the EGU following this, where it showed that the two melt episodes at Summit Station essentially preconditioned the ice so that there was limited ventilation into the firn from aloft. This affects in the chemistry profile through the firn as well as heat transport in the snow and ice. And then there was 2021. You get the impression things are picking up over the Atlantic. And there are 3 episodes that summer of major melt over Greenland. And what was interesting was the 14th of August rain case, which had its origins in an atmospheric river. This is a picture taken by the staff at Summit Station. You can see the rain on the window there of the building. And what happened in that case was this atmospheric river came up the west coast. This is the day earlier. And then the moisture spread over the ice sheet. And you can see the back trajectory from here on the south coast, where in fact it's tapping into the tropics once again. So again, we have these large scale events, atmospheric rivers, and a source of moisture to the south. What's interesting is this event was forecast 5 days ahead of time. This is from the Center for Western Weather and Water Extremes at Scripps, where they do the IVT, Integrated Vapor Transport with the GFS. And this was 5 days ahead of time. It was showing this massive transport of moisture around the high in the Atlantic, then up into Greenland. And that was what then brought the warm air warm enough to rain at Summit Station at 3 kilometers above sea level. And what hurricanes might take away in terms of melting the ice, hurricanes can also deliver more precipitation, more mass to the ice sheet. This was Hurricane Larry on the 12th of September last year that brought 2 to 3 feet of snow to the ice sheet. So one hurricane taketh, another hurricane giveth. So the question is, are these recent events indicative of fundamental change in Arctic weather? So we looked into the past. In our 2014 paper, we looked at July of 2012 and July of 1889. In both cases, we found these atmospheric rivers from the 20th century reanalysis. And what we found was that 20th century reanalysis captured the essence of the atmospheric rivers and their impact on Greenland. So we went back to 1920, asking, in fact, where does the present fit in the context of the past? And these are the number of atmospheric rivers each summer going back to 1920 from using our criteria applied to both the 20th century reanalysis and more recently to era 5. And what you see is, in fact, there's not much of a trend there. It goes up and down a bit. And so we asked, well, if atmospheric rivers aren't changing in frequency, what is? That particular extreme there is because they're multi-day episodes that adds to the count. What we found when we looked at the temperature is it was warm back in the early 1930s and then cooled off for many decades and then started warming again after 1990. And you can see the rapid rise then over the last 20 years from the 20 CR. When you look, and this is a pretty good episode, that was just before the Dust Bowl in the central North America. Now, this is the integrated water vapor through that same period. And along with warmer temperatures, you see increased water vapor. This is all on Greenland. This is moisture going to Greenland. And what happened was that during this increase in moisture going to Greenland, there was an increase in atmospheric rivers during that time. Asking, is it reasonable to use the 20th century analysis, look at the past? This is from our 2014 paper, where we saw a very good correlation between station data from Ulasat along the west coast of Greenland and the 20 CR. The red is the station data, the black is the 20 CR, which is a little more smoothed out. But then it turned out there's ice core data from the Nîmes site, and this is a very nice analysis done by Valérie Masson-Thomas from Paris, where she looked at the delta oxygen 18, which is a measure of temperature in the ice core, and going back in time. And in fact, if you look at this inset here from 1920 to the current, is in fact the temperature in the ice core from delta 18 oxygen. It matches up very well with the 20 CR. So it's a very nice correlation between the ice core data and the 20 CR. So our takeaway message is, one, our simple atmospheric river detection method works fairly well. Multi-day episodes tend to overcount AR events. The method also reviews reveals smaller scale transport of moisture in the melt regions at the end of the AR life cycle. So we may not have a fully blown atmospheric river impacting Greenland, but we have the aftermath of the atmospheric rivers that have to be accounted for. And furthermore, these recent melt events reflect transport of heat from other continents, just not North America, as in 1889 and 2012. An assessment of the potential role of areas of increased heating over the continents from climate models seems prudent. The 20th century review also produces time series of temperature and integrated water vapor to 1920, consistent with ice core data from the NEAM site. This suggests more use of ice core data, 20 CR, as well as station weather and water vapor isotopes in assessing trends in Greenland climate. And then finally, almost finally, hurricanes increase the melting of the ice sheet through increases in rainfall, sensible late heat transfers, the possibility of shifting storm and hurricane tracks in the North Atlantic should be examined with models more thoroughly. There's some recent results from GFDL suggesting, in fact, possibility of the hurricane track shifting more northward in the Atlantic. Also, late season hurricanes such as Larry in 2021 should be monitored for their effect on mass increases on the ice sheet versus the early season hurricanes that can accelerate mass loss. And finally, in the supplemental material which follows, we show I'll show one of the after things, after events, showing what happens after initial AR event. And in this case, this shows at the time of the atmospheric river, and then 3 days later. And what it shows is the ridge that impinges on the southeast coast of Greenland shifts to the east, the winds shift to the east, and the integrated water vapor shifts to the east, but leaves a residue along the west coast. The importance of that is the warm air and the moisture and clouds sitting along the west coast can continue to melt ice, even as the atmospheric river system has moved on further east. So I think I'll quit at that point.
Great, thank you very much, Bill, for that really nice overview. Clearly, there are a lot of things going on, a lot of pieces coming together, and seems to be a lot of impact. So I'm going to open up the floor for questions. See, there's one new message in the chat. Oh, it's a thank you note from Barry. Any questions from the group or comments? Well, maybe I'll start with a naive question, but clearly we've heard a lot about how there are projected changes to things like the Gulf Stream, hurricane intensity, hurricane frequency, general synoptic flow, and I wonder if you have attempted at all to try to connect the dots between all of these anticipated or projected changes and the sorts of events that you're evaluating here.
My first comment, and this is based on work I did in Antarctica several decades ago, is that a decay does not a trend make. And you have to be very careful about interpreting trends at 10 years. The best way to stop a trend is to publish a paper on the trend. And we discovered that early on. So I think it's a matter of, keeping the observations going, looking at the observations that can tell you more about the energy balance of Greenland, and then use the models judiciously to, one, anticipate what might happen, and then to deploy observations, make sure you have the observations necessary to gauge those projected changes versus reality.
Thank you. It looks like Rudra has a question. Rudra, go ahead, please.
Yeah, hey, that was a really interesting talk, and I actually kind of have a very basic question. That while working on the Greenland, have you ever seen that probably any location in the Greenland, maybe the west or the east, where you see frequent ARs happening, and if you find something like that, like probably west of the Greenland are having more ARs, do you think there is a physical process that could explain that weighting, that why is it more frequent towards one side and less frequent towards the other side?
I've not looked at that. I think that's one of the next things I want to do. I mean, I've done this primarily for the West Coast because that's where the major mass loss is. But what I want to do is do a similar sort of analysis for the anticyclonic wave breaking and the transport to the east. And so that'll be sort of the next thing I play with in my spare time.
Thank you, Bill, and thank you, Rudra, for the question. Hai Long, go ahead.
Yeah, thank you, Bill, for the very nice presentation. I wonder if you also looked at the, related to the previous question, from the transport of moisture from or AR from the other side sector, like Pacific sector, is that much less important, particularly to the Greenland ice melting?
Definitely not from the Pacific sector, although what Lance Bosart showed is that the dynamics of the atmosphere far to the west influence what happens to Greenland, and particularly that case in June of 2019. It was essentially what happened at the exit jet across the Pacific then excited a wave, which then actually picked up a residual typhoon, actually a hurricane in the Gulf, which then amplified and brought moisture up into over the maritime provinces of Canada. So the atmosphere is very interconnected.
Yeah, another quick follow if it's allowed. Have you also looked at the elevation? Mostly, you're looking at the column integrated, but for impact on Greenland, maybe elevated moisture sources may be more important if they're originated from further to the tropics, might be transported at the higher elevations. Are those more important for the Greenland?
Yeah, but I think there's two parts of that. I did look at the specific humidity on fixed levels, and essentially it's fairly coherent with height up to 700 hectopascals. But what happens oftentimes in terms of the dynamics over the ice sheet, once the food number is sufficient that the flow along the coast can lift over the ice sheet, you get interesting effects as the air moves up over and, for example, rains out, releases latent heat, et cetera, going over the ice sheet. And there's a new project that's been started called Ice Caps Melt, where instruments will be deployed at mid-level and primarily in the ablation zone of the ice sheet that can perhaps shed information on what's happening en route to the highest parts in the accumulation area.
Great, thank you very much.
Thank you. I see Christine and Kyle both have hands up, and there was a question in the chat. I'm going to call on Christine to ask her question, and then maybe Kyle, if it's okay with you, can you post your question in the chat so that we can make sure Michael has enough time for his presentation as well? Christine, go ahead.
Thanks, Bill. That was a really nice presentation. So I have a question. This is probably just based on your years of experience looking at this. Do you have a sense for what is the net, what is the predominant impact? Like, are there more melt events than accumulation events? And if so, like, is it west versus east Greenland, or what is your sense on the general impact on the ARs in terms of like an overall estimate?
Yeah, I don't myself. I think Kyle Madley's paper addressed some of those issues, and particularly in terms of the west versus east. The cases in the east tend to have colder air and more accumulation. On the west, it's warmer air, more melting. But there are also issues in the future related to what are called tipping points, because right now a lot of the mass loss is due to glaciers losing ice into the ocean. At some point, once the glaciers stop losing ice, then you have to look to warming to continue the runoff from the ablation zone. And so we have an interesting future ahead of us.
Well, thank you. I'll be sure to read Kyle's paper.
Yeah, the 2018 paper is really nice in that respect. And Kyle, if he's there, can probably comment on that also.
I think he is. Thanks.
Thank you for the question, Christine, and thanks, Bill, for your wonderful presentation and for all this discussion. As I mentioned, there is a question in the chat already from Mindy Brigman, and then also I think Kyle is going to follow up with a question as well. So I encourage people to check the chat for additional follow-up. In the meantime, we're going to switch over to our next speaker, and that is Michael Tjernström from Stockholm University. And I think that the the level of discussion here indicates very nicely how much excitement there is in the community about these types of events. And Michael's in the process of spinning up a new field project that is aimed at understanding the influence of atmospheric rivers on sea ice melt. So Michael, thank you for joining us, and please go ahead with your presentation.
Thank you, Chris, and thanks for having me and inviting me. So I'm going to be presenting here the Art of Melt field campaign. And Art of Melt is the atmospheric rivers and the onset of sea ice melt. So there's two parts to this. And I start by showing a very, very old annual cycle of near surface temperature, which is taken from Shiba. There aren't too many Central Arctic annual temperature series. We now have Mosaic, but when I did this slide, that wasn't out yet. So you can learn a lot about the climate in the Arctic by just looking at the temperature time series, and you can see in the winter it swings widely between -20 and -40. In the summer and during the melt season, stuck around zero for quite some time, and there's been some interest lately on the shoulder seasons. What happens when the freeze starts in the fall, and what happens when the melt starts in the spring? For various reasons, there's plenty of observations of the freeze onset, including Shiba and a number of other campaigns, Mosaic possibly even twice. But when it comes to the melt onset, there is not too much. There is the Shiba experiment, there's Norwegian N-ice in 2015, and partly Mosaic. Actually, due to the pandemic, the Polarstern had to leave the ice when the melt onset happened. So why do we want to know when the melt onset happens? Well, the length of the summer melt is of importance for the summer sea ice and for the amount of ice you have at the end of the summer. And understanding what triggers the melt facilitates more accurate seasonal prediction of sea ice, for one. And the distribution of sea ice in summer is also important for understanding extreme weather. So if you look back at satellite data and what's happening to the onset of this melt, you can see for the blue line here is the Greenland Sea, a rather large area. So it's probably a lot of variability, but the red line is for the Central Arctic. The dashed line indicates when any of the pixels in that area starts to melt, and the blue line is when the whole area starts to melt. So you can see that from the beginning of the 80s and up until the last decade or so, it's starting to happen something like 20 or 30 days earlier. We want to marry that concept with the atmospheric rivers, and Bill gave us a very nice outline for what this is. Essentially, you have like a filament or a stream of warm and moist air that enters in over the Arctic. And when this happens in spring, the warm and moist air is rapidly cooled down by the presence of the sea ice when you come in over the Arctic. And clouds form, it changes the surface energy budget, it changes precipitation, etc., as the air is transforming from mid-latitude to Arctic air. And to the left there, you see one such event that happened during the Mosaic on the 16th of April. And it shows the integrated water vapor, and the red dot in here is actually the position of Polarstern before she had to leave the ice. These events have a pretty dramatic impact on what happens to the local climate or the local weather in the Arctic. This first one that happened on the 16th of April raised the near surface temperature by 10 degrees per day. The temperature went up from -30 to close to zero in 3 days. So that's a pretty dramatic change. Then it went slightly back again, and then the next episode came And you could, with a little bit of imagination, see the structure of the old one having drifted away to the east. It's important to remember here that these are not trajectories. It's easy to sort of imagine that the air is streaming north in these filaments, but at the same time, the filaments are also moving. So the hypothesis behind the whole expedition is the following. So in early spring or early summer, the surface albedo is very large and the solar radiation is weak, so that net surface solar radiation is small. When one of these atmospheric rivers happen, it will bring warm and humid air, often with clouds, and you may see this famous shift of net long wave radiation from -50 to near zero. So you can easily have an increase in net long wave radiation by 30 to 50 watts per square meter. This air is also warm compared to the surface, so you might add anywhere from 10 to 30 watts per square meter in turbulent sensible heat flux of air. And if this is sustained over several days, you raise the surface temperature from cold winter temperatures to the melting point, and snow starts to age first, and then it starts to melt, and melt ponds form. And if this can happen for a sufficiently long time, the surface albedo will decrease rapidly. If conditions are right, if it's sufficiently late in the season, this may change the net solar radiation at the surface such that even if the warm air moves away, the surface energy budget might have been irreversibly changed to positive, and that's when melt has started. This is actually from Mosaic, courtesy of Chris Cox. The two events that you saw in the previous slide are these two. The rest of this episode is covered by a surface energy budget station that was left in the ice as Polarstern went out. And you can see that there are 1, 2, 3, 4 more of these. And in each case, the surface temperature goes up rather abruptly, but it's not until in here in May that it stays melting. To the left, to illustrate a little bit about the surface albedo thing. Now, this is in August, was the only photo that I could find, but you could see a rather dramatic change in surface albedo once the melt ponds come out. This graph shows satellite information about the melt onset. It has a number of dots for each year, where the blue dot, the light blue dot here, is the median date across this map up here. Then you have the 75 and the 95, the 5 and the 25 percentiles. So you have really early dates in here and late dates in here, and there's a distribution across the Arctic depending on the year. Now, if you take the anomalies in long wave radiation down and short wave radiation down, and in this case, the integrated water vapor in kilograms per square meter, and you shift the timing so that for each grid point, each pixel, it happens on the date of the melt onset, you can see that there is a clear link here between the anomaly in long wave radiation or in water vapor caused by an intrusion of warm and moist air and the melt onset date. That signal is strongest when the melt onset is early, and it's weakest when the melt onset is late. But you can see here the anomaly in long wave down is easily 10 watts per square meter across all the different median points. And there's quite a substantial increase in water vapor when the melt happens. So what are we going to do? Well, the strategy is the following. We will take the Swedish icebreaker Odin and deploy her somewhere in here early in the season. We will then use ensemble forecasting from the European Center for Medium Range Weather Forecast. An example shown here for the episode that happened during Mosaic shows the extreme forecast index for water vapor, integrated water vapor. Once we know approximately where to expect an event like this, we'll use forecast trajectories to pinpoint an optimal location and then simply navigate the icebreaker to the location and wait for the warm and moist air to arrive. Most of the observations will be carried on board the icebreaker because we want to be able to position ourselves in an optimal place. So therefore, we do not plan to build an ice camp like many other expeditions like this. We will stay mostly on board. The icebreaker is equipped with a lot of instruments, a lot of remote sensing and regular weather station and aerosol information on the 7th deck, 6 hourly releases of soundings from the helipad. And on the foredeck, we have cloud radar, microwave radiometer, and we also do continuous eddy covariance surface flux observations. So that means that together we can measure all the different terms of the surface energy budgets from the ship. We also often do trace gas fluxes, combining the sonic at the top of this mast with other instruments that can measure carbon dioxide or methane or other trace gases. We will also have a fairly complete set of aerosol instruments. This is the new Stockholm University aerosol container that will come along. It's not on this picture, obviously, but have air inlets, both for total air, but also for cloud, the counterflow virtual impactor to sample just the cloud particles separately. And inside, there's a lot of instruments to analyze the details of aerosol chemistry and aerosol physics. We will not build an ice camp, as I said, but we will do additional measurements from the ice and also from the icebreaker. The rule then, or the principle we'll try to stick with, is that whatever you put on the ice will have to be able to put back on the icebreaker within 1 day so that we can move. We plan to do tether soundings from the icebreaker. We'll do chamber fluxes of trace gases from melt ponds, from leads, and also from the snow and ice on the surface. And we'll do water column observations from the icebreaker, water sampling, but also CTDs. And whenever possible, we'll put up surface energy budget stations on the ice as we're staying more than a few days on a certain location. I listed some of the science questions that are probably pretty obvious. What are the conditions for episodes to trigger melt? What processes dominate the surface energy budget? An obvious candidate is the long wave radiation, of course, but I personally think that sensible heat flux might be important as well. We saw today on the Mosaic workshop where I am that the conduction of heat through the ice is also very important. We also heard that one of these events actually did melt a little bit, one of the early events during Mosaic. So does refreezing happen after the melt has started, and why does it happen if it does? What is the vertical structure of these atmospheric rivers, phase partitioning, radiative effects of clouds? And what else is coming with these atmospheric rivers except for water vapor and clouds? What does it do to the atmospheric chemistry, to aerosols, pollution, etc., etc.? This is work in progress, obviously. We've had 2 online scoping and planning workshops, each with about 50 participants. We have 22 projects that has been announced from 13 universities and 7 institutes from 10 different countries: Norway, Denmark, Finland, US, UK, Canada, France, Switzerland, Germany, and obviously Sweden. Many have pending grant proposals. So exactly the composition of the science program will have to await until we know exactly who is funded and who's not funded. Next workshop will be in the fall of 22. That will be the so-called scope of work workshop. that would be an in-person workshop where we'll get together and lay out the details of the actual logistics, the planning, how it will be done. And the plan is to mobilize on Odin in April of 2023, leave Sweden early in May. Probably the science team will depart from Tromsø around the 4th or 5th of May and come back to Tromsø or possibly Longyearbyen around 20th of June. So that is the plan, and I thank you for listening, and I'd be happy to take any questions.
Excellent. Thank you very much, Michael, for that nice presentation. We have a little bit of time for discussion and questions. Any questions from the group? Long, please go ahead.
Yeah, thank you, Michael. Very exciting project. So you listed like collaborators from 10 countries, including from US. I wonder, so because our project funded by DOE, Readiness RGMA program area, has a small element of focus pretty close to this science objectives. I wonder, what is there any way to just collaborate on doing the science, not joining the field campaign measurements, but maybe as a user or whatever revenue you may support?
Absolutely. Yeah, absolutely. Send me an email. I'll fill you in. So we're very, I mean, for participating in the field work, it's getting to be late to take new projects on board, depending a little bit on what happens to the grant proposals. But collaboration, absolutely, sure. Everyone, I think, is eager to collaborate as much as possible, and I'd be happy to get in touch with you.
Great, thank you very much.
Michael, is it okay with you if I put your email address in the chat?
Yes, that's fine.
Great, thank you.
All right, great. Thanks, Long, for that question. I know we have a few other groups who are traditionally on the modeling side of the house, and clearly there's some interesting opportunities here to try to understand maybe some of the things that are observed during Art of Melt. Are there other questions from the group? Or yes, Rudra, go ahead.
Yeah, based on your talk, I had two different questions. One, I myself am working on ARs in the Arctic with Christine Shields and Steve Weber's here in the group. So my question was that we have been observing that ARs during the winter are also more effective and like more increasing in the frequency, as well as they also cause sea ice loss in the Arctic. Are you planning to, like in the summer, what happens is that the moisture inherently is so high that there's already ice melt going on. Whereas it's more interesting to study in the winter where it's like a growing season, but you have an AR and then some sea ice might happen. So are you planning to do a winter observation expedition as well, or it's going to be much summer focused?
I wish I could do a winter expedition, but the layout with the use of Odin as a research icebreaker is that it's used in summer. So we're actually the first one that can use her as early as this. In the winter, typically, otherwise, Odin is an assistance icebreaker for the commercial shipping in the Bay of Bothnia. So that would not be possible. But you bring up an interesting aspect. These atmospheric rivers have very different impact during different parts of the year. So in winter, it's very difficult to see how it would bring the ice to melting. I mean, it might do so for a very short time period, but it can't be sustained. But on the other hand, it will reduce the freezing, so it will have an effect accumulated into the season. In summer, there's actually an increase in atmospheric rivers also. However, that's from Siberia out over the Russian shelf. So there's an increase in the northern North Atlantic in winter, and an increase in summer over the Siberian continent. That air is often very warm and very moist, and when that comes out over the melting sea ice, you generate extremely stable conditions with very strong surface inversions where the air is several degrees warmer. I mean, we've seen one case where you had plus 15 degrees at 200 meters and 0 degrees at the surface. That generates an enormous long wave radiation flux, and that definitely affects the melting. So, but it's different. And in this particular campaign, we're targeting the melt onset simply because there's hardly any observations of the melt onset in situ.
Yeah. That is very true. I was not familiar with the concept of ARs and the melt onsets, but that's very interesting to know. Looking at sea ice loss in the Arctic, I can email you later on for sure if any other people have any questions and would like to know more about your expedition as well. Yeah. Thank you.
Very good. We're quickly approaching the end of our meeting, but I see Steve has a hand up. So Steve, if you have a somewhat short question, please go ahead.
A fairly short question. Michael, very nice talk. Your results, as I understood them, relating to the timing of the melt onset, relating those to radiation parameters, long wave, short wave, water vapor, that was for the whole of the ice domain, wasn't it? Your average over your...
You mean, well, I think that could act locally as well, I think. But I think the earlier melt onset you have, the stronger the signal seems to be from the satellite data. But I just in general, I think if you can change the albedo sufficiently and you're sufficiently late in the year, so you have some solar radiation, then you could actually turn the switch. I think the thing that changes, the thing that's different from how you and I think about spring or autumn, that also for that matter, is that it's not a gradual thing. It's not that something that goes on for a month, going from winter to summer. It's something that happens in a very short time period. And the albedo, I think, is the key, both in the spring onset and in the freeze up in the autumn, but in different ways.
Yeah, I was just wondering if there were certain regions that there was higher sensitivity compared to other parts of the Arctic, if you've broken it down that way.
I haven't broken it down that way, but my gut feeling is I think it would be more sensitive the further south you go, of course, because the further south you go, the more solar radiation you would have earlier in the season. So I think that would make a difference.
Okay, thanks.
Very good. So we are now very close to the end of our meeting. I wanted to check in with Hazel and Cynthia to see if there are any messages from the secretariat for Icebreaker. I know we're still working to move towards the official implementation plan for the new research plan. So any news from the secretariat that should be shared with the group? And no is an okay answer, but thought I'd give the opportunity.
Nothing from me at this point. Thank you for a really interesting meeting. As Cynthia mentioned at the beginning of the call, the recording will be posted on the Icebreaker website and on the YouTube channel. And if you haven't checked out the YouTube channel, there's a specific playlist for the atmosphere collaboration team and a lot of interesting content there. So thanks again, Cynthia, if you have anything else.
Yeah, nothing from me as well. Really engaging, really great talk. So really enjoyed the session. Thank you.
Great. Well, thank you everybody for attending. Thank you to Bill and to Michael for their presentations. I encourage everybody to keep talking about this subject. Clearly, there's more to come in the coming weeks and months and years ahead as Art of Melt hopefully takes off and provides a whole new data set for us to understand these processes. So thanks everybody for joining. Hopefully we will see you all next month when we meet again. And yeah, thank you. Have a great week.